All right, let's talk about something super basic, adding two numbers. I mean, you've been doing it forever, right? But what if I told you we're going to do it the hard way? Yeah, we're going to see how this simple, everyday task turns into a really cool computer science puzzle, all because of one little twist. So how on earth does adding two numbers become a big problem? Well, it all boils down to this fundamental clash between how our brains are trained to do math and how a very common data structure actually works. And here it is, the problem in a nutshell. Think about how you add numbers, say 123 plus 456. You start with the 3 and the 6 on the far right and work your way left. But a linked list, it's a one-way street. You start at the beginning, the head, on the left, and you can only move forward, to the right. There's no jumping to the end, no going backward. And that is the core conflict we have to solve. This brings us to the official problem, often called add two numbers 2. We get two linked lists, each one representing a number. But this part right here is the kicker. The most significant digit comes first. That means the numbers are stored just how we'd read them, which is great, but it's the exact opposite of how we need to add them. So for this explainer, we're going to be working with this example right here. The first list is basically the number 7,243. The second one is 564. Our job is to add them up and spit out a brand new linked list that represents the correct sum. And this is what I like to call the linked list dilemma. Why can't we just, go through both lists at the same time and add the digits as we go? It seems so simple. Well, this question is exactly why the simple approach completely falls apart. When you're adding and a column goes over 9, you have to carry the 1 over to the next column, which is the column to the left. But if we're moving left to right, that column is one we've already finished with. And this makes it crystal clear. Let's look at our example. If we just started from the left, we'd do 7 plus 5. That's 12. So, is the first digit of our answer a 1? No, the final answer starts with a 7. The math is totally wrong, because a carry from a later column needs to affect this first one. We basically need information from the future, and with a linked list, there's no going back in time. So if moving backward is impossible, what do? We need a trick. We need some way to flip our perspective to reverse the order without actually reversing the lists themselves. And this is where a really elegant data structure saves the day. The stack. This is the exact question the stack was practically invented to answer. We're stuck reading left to right, but we desperately need to do our math right to left. A stack is the perfect tool to bridge that gap. The easiest way to think about a stack, just picture a stack of plates at a buffet. You put a clean plate on top of the pile. Where does the next person grab a plate from? The top, of course. The last one you put in is the first one they take out. LIFO, last in, first out. That's it. And this simple idea is exactly what we need to crack this problem. So here's the game plan, just 4 simple steps. First, we'll just read through each list one by one and push every digit onto its own stack. So for our number 7243, we'll push the 7, then the 2, then the 4, and finally the 3. The 3 will be sitting right on top. Then we just loop, pop the top numbers off, add them up, and build our result list. Okay, let's actually do this. We've got our plan, we've got our example. Now let's put it into action. This is where it all comes together. Right, here we go. Our stacks are loaded up. Stack 1 has the 3 on top, stack 2 has the 4 on top. We'll also keep track of a carry variable, which for now is just 0. So let's pop them off. The math here couldn't be easier. We pop the 3, pop the 4, and add our carry, which is 0. That gives us 7. Since 7 is less than 10, there's no new carry to worry about. The value for our new result node is just 7. And just like that, we create the very first node of our answer. It's a list with a single node containing the number 7. So far, so good. Let's do the next one. Okay, now things get a little more interesting because you're about to see the carry in action. We pop a 4 from the first stack and a 6 from the second. And remember, the carry from our last step was still 0. So we add them up. 4 plus 6 plus 0 equals 10. Now for our result, the node's value is the remainder, which is 0. And the new carry, that's the 1 from the 10. This is literally carrying the 1, just like we did in grade school. Okay, now this is the other really clever part. We don't stick that new 0 node at the end of our list. No way. We put it right at the front. It's called prepending. So our list, which was just 7, now becomes 0, 7. You see what's happening? We're building our answer backward.
which is exactly what we need to get the number in the right order at the end. It's perfect. Let's just blast through the last two steps. For step 3, we pop 2 and 5. Oh, and don't forget our carry is now 1. So 2 plus 5 plus 1 is 8. We prepend the 8 and our list is now 807. The carry goes back to 0. For the final step, stack 2 is empty, so we just pop the 7. Add our 0 carry, we get 7, prepend that, and boom, our final answer, 7807. So let's step back. What did we really just do? We were faced with a problem that looked kind of impossible because linked lists only go one way, but we found a really clean, elegant way around it.
You know, the problem description even gives you a little hint with this follow-up question. See, a different approach might be to just reverse the lists first, but that's messy. It changes the original data, and a lot of times you're not allowed to do that.
And our answer to that question is a huge yes. That's the beauty of the stack. It gives us a virtual reversal. We get to process all the digits in the exact reverse order we need to, but we never had to touch or modify the original lists at all. It's just clean. And this is bigger than just one coding problem. This is a powerful pattern you can use everywhere. Anytime you run into a situation where the way you get the data is the opposite of how you need to process it, things like parsing code or an undo function in an editor, a stack should be the first thing that pops into your head. So, I'll leave you with this final thought. The stack let us solve this whole thing by essentially thinking about it backward. It flips the problem on its head. So my question to you is, what other crazy, impossible-looking problems out there might just clip if you stop, change your perspective, and try starting from the end?